This is a video presentation on Chapter 8, Fuel Cell. We will discover fuel cell introduction, simultaneous heat and mass transfer in porous medium, diffusion in a moving medium, design of heat and mass transfer equipment. First, we will cover about fuel cell introduction. This is a simple introduction. Fuel cell vehicle, the short form for fuel cell vehicle, which is FCV or FCEV. The example of vehicle that use fuel cell is Toyota Mirai or Hyundai Nexo. What is fuel cell? A fuel cell is a device that converts chemical potential energy, which is energy stored in molecular bonds, into electrical energy. A PEM or proton exchange membrane cell uses hydrogen gas, which is H2, and oxygen gas, O2, as fuel. The products of the reaction in the cell are water, electrical, and heat. This is a big improvement over internal combustion engines, coal burning power plants, and nuclear power plants, all of which produce harmful byproducts. This is fuel cell schematic. In the first case, the oxidant at the cathode combines with the electrons, which tend to circumvent the electrolyte, and becomes anions which travel through the electrolyte to the anode. At the anode, the anions give up their electrons and combine with hydrogen to form water. The water, depleted fuel, and products are exhausted from the anode surface, and the depleted oxidant and products are exhausted from the cathode surface. In the second case, where the electrolyte conducts cations, the hydrogen-containing fuel is decomposed electrochemically, giving up electrons and leaving up hydrogen cations to travel through the electrolyte. Upon reaching the cathode, the cations combine electrochemically with the oxidant and electrons, which tend to circumvent the electrolyte to form water. This is the description about the schematic diagram I just talked before. There are several types of fuel cells, and they belong to either of two cases just described. First, anion conducting electrolyte fuel cells, which is alkaline fuel cells and solid oxide fuel cells. Second one is cation conducting electrolyte fuel cells, which is phosphoric acid fuel cells and polymer electrolyte membrane fuel cells.
Okay, this is simultaneous heat and mass transfer. What is heat transfer? Heat transfer is the change of thermal energy between physical systems. The rate of heat transfer is dependent on the temperature of the system and the properties of the intervening medium through which the heat transferred. The three fundamental modes of heat transfer are conduction, convection, and radiation. Okay, now is mass transfer. What is mass transfer? Mass transfer is the net movement of mass from one location, usually meaning string, phase, fraction, or component, to another. Mass transfer occurs in many processes such as absorption, evaporation, absorption, drying, precipitation, membrane filtration, and distillation. Mass transfer is used by different scientific disciplines for different processes and mechanisms. Okay, now is simultaneous heat transfer, heat and mass transfer. Heat transfer is only by conduction in opaque solid, but conduction and radiation in semi-transparent solid. A solid may involve conduction and radiation but not convection. A solid may involve convection and radiation on the surface exposed to the fluid or other surface. Heat transfer is by conduction and possibly by radiation in still fluid, no but fluid motion, and by convection and radiation in a flowing fluid. In the absorption of radiation, heat transfer through a fluid is either by conduction or convection depending on the presence of any bulk fluid motion. So the convection equal to conduction plus fluid motion. Heat transfer through a vacuum is by radiation. Most gases between two solid surfaces do not interfere with radiation, so the liquid are usually strong absorber than radiation. As we can see in the picture, although there are three mechanisms of heat transfer, a medium may involve only two of them simultaneously. Okay, this is simultaneous and mass transfer. Mass transfer process encountered in practice occur isometrically and thus they not involve any heat transfer. But some engineering applications involve the evaporation of a liquid and the diffusion of this vapor into a surrounding gas. Such process required the transfer of the latent heat evaporation HFG to the liquid in order to vaporize, and thus such problem involve simultaneous heat and mass transfer. To generally, any mass transfer problem involves phase change, evaporation, sublimation, condensation, melting, and others. Must also involve heat transfer, and the solution of such problem is to whether analyze considering simultaneous heat and mass transfer. So we can see in the picture many problems encountered in the practice involve simultaneous heat and mass transfer.
Now we will continue the video by the chapter about the mass transfer in porous medium. So, what is a porous medium? A porous medium or media are a solid materials that are composed of pore structures. A pore structures mean that the surface have a pore or a holes, such as in the picture, like the sponge. So, some applications such as in fuel cell, digestive system, or building materials require a detailed analysis of convective heat transfer in different shapes, orientation, and configuration. In 2007, Azim et al. States that there are many physical phenomena that can be coupled with heat transfer in porous medium, and one such phenomenon is heat and mass transfer resulting due to the diffusion of mass under the influence of heat. So, heat and mass transfer in porous medium can be easily described by three sets of partial differential equation (PDE), which is the first one, the momentum equation, the second one, energy transport equation, and the third one is the mass diffusion equation. So, let's see the equation. This is the three equation, which is for the momentum, energy equation, and the equation for species concentration. Basically, this equation is in non-dimensional form. So, for this chapter, we just look the equation for the mass transfer only, which is the bottom one, which is delta C over delta Y times with delta C over delta X minus delta C over delta X times with delta C over delta Y equal to 1 over LE times with delta squared C over delta X squared plus delta squared C over delta Y squared. So after that, from the equation, we convert the equation into a set of algebraic equation using linear triangular elements. The result which is been shown, which is the RE is equal to blah blah blah. Next, we convert the equation from before into a set of algebraic equations using linear triangular elements, and the result have been shown in the video. So the RA, which means the Rayleigh number or the fluid velocity, RD, which is the radiation parameter, and the buoyancy ratio, and LE, which is the Lewis number, which is equal to 10, which been used in the equation. Next, we differentiate the equations and it will become like this. And from the alphabet that been given, which where the B and C are given as like on the right side, which is the B, C, for the I, J and K. Then from the equation, it can conclude into a graph, which shown here. Basically, the graph shows that low Rayleigh number shows that the solution is stable, and the lower Rayleigh number, radiation parameter and buoyancy ratio will lead to achieve faster convergence, which means by lower Rayleigh number, the mass and heat transfer in the porous medium become more rapid. So this is the reference for this subchapter. Okay, so that's all from this chapter. Blah, blah.
I will continue on diffusion. First, what is diffusion? Diffusion is a net movement of anything, example atom, ion, molecule, from higher region concentration to lower concentration. Diffusion is driven by gradient in concentration as shown in figure beside. Okay, now I will continue on gas diffusion layer. The gas diffusion layer electrically connect the catalyst and current collector. It must be porous, electrically conductive, and thin. The reactant must be able to reach the catalyst, but conductivity and porosity can act as opposing forces. Optimally, the gas diffusion layer should be composed of 1/3 Nepean or 15% of PTFE. The carbon particle used in GDL can be larger than those employed in the catalyst because surface area is not the most important variable in this layer. Gas diffusion layer should be around 15 to 35 micrometer thick to balance needed porosity with mechanical strength. Often, an intermediate porous layer is added between the gas diffusion layer and catalyst layer to ease the transition between the large pores in the gas diffusion layer and small porosity in the catalyst layer. Since a primary function of the gas diffusion layer is to help remove water, a product flooding can occur when water excessively blocks the gas diffusion layer. This limits the reactant ability to access the catalyst and significantly decreases performance. Teflon can be coated onto the gas diffusion layer to limit the possibility of flooding. Several microscopic variables are analyzed in the GDLS, such as porosity, totality, and permeability. These variables have incidence over the behavior of fuel cell. Two major gas diffusion layer substances are carbon cloth and paper, were compared indicative of different cell performance. Okay, next I will explain the main function of gas diffusion layer. First is a gas diffuse pathway from flow channel to the catalyst layer. Second, help remove byproduct water outside of catalyst layer and prevent flooding. Next is keep some water on surface for conductivity through the membrane. Fourth is heat transfer during cell operation, and the last is to help provide enough mechanical strength to hold the
MEA from extension caused by water absorbency. Next, the video will explain more about the gas division layer.
The reactant gases coming from flow-filled plates get into the gas diffusion layer GDL. The GDL is a porous material that ensures the reactants, in this case hydrogen, diffuse to the catalyst layer. The GDL is made of carbon fibers, and in this scene represents a scanning electron micrograph image. The GDL is typically wet-proof with a Teflon coating material to ensure that its pores do not become congested with liquid water. In this way, the GDL assists in water management by allowing an appropriate amount of water to reach and be held at the membrane for hydration. At the anode catalyst layer, the reactant stream, consisting of hydrogen and water vapor, dissolves into the liquid electrolyte to finally arrive at the electrode surface, where they are absorbed. Absorbed species might migrate on the solid electrode surface, mainly by diffusion. The reaction gives rise to protons and electrons.
Next is fusion gas division layer based material. Fusion gas division layer based material GDL is a multifunctional material used to supply hydrogen and air or fuel to the electrode, or in this case is catalyst, collect electron produced by the chemical reaction with the electrode, and drain moisture on the electrolytic membrane and water generated by processes. Carbon paper and carbon cloth is generally used due to various requirements including gas permeability, conductivity, and acid resistance and mechanical strength as shown in the picture beside. Okay, next I will explain on the reaction in PEM. First, a proton action membrane fusion PEMFC transform a chemical energy liberated during the electrochemical reaction of hydrogen and oxygen to electrical energy as opposed to the direct combustion of hydrogen and oxygen gases to produce thermal energy. The first reaction happen at anode, which are a stream of hydrogen is delivered to the anode side of the MEA. At anode side is critically split into proton and electron. This oxidation half-cell reaction of hydrogen oxidation reaction HOR is represented by the formula beside the chemical reaction beside. H2 is equal to H2 H plus and 2 electron. At cathode, the newly formed proton permeate through the polymer electrolyte membrane to cathode side. The electron travel along an external load circuit to the cathode side of the MEA, thus creating the current output of the fuel cell membrane. Meanwhile, a stream of oxygen is delivered to the cathode side of the MEA. At cathode side, oxygen molecule react to proton permeating through the polymer electrolyte membrane and electron arriving through the external circuit to form water molecule. This is reduction half-cell reaction or oxygen reduction reaction. ORR is represented by the chemical reaction beside which produce water. And overall of this reaction is the reversible reaction is expressed in the equation as shown. The reincorporation of the hydrogen store an electron together with the oxygen molecule and the formation of one water molecule. The potential in each case are given with respect to standard hydrogen electrode as shown in the chemical reaction below. Now, this video will show how the PEM fuel cell works.
Okay, I will talk about the design of heat and mass transfer equipment in the fuel cell. For the system design of a fuel cell, it can vary from very simple to very complex. That depends on the fuel cell application and the system efficiency that the researcher want or the company want. And then the fuel cell catalyst, membranes, and flow field plates are very important areas for fuel cell improvement. But the most important thing is the stack optimization, because most of the fuel cell use stack. Some of the design consideration for fuel cell system is the electrolyte substance, which is easily defined as the type of the fuel cell. Can be made from potassium hydroxide, salt carbonates, and phosphoric acid. Next is the fuel that was used. Most common fuel cell use hydrogen. Next is the anode catalyst, usually made from fine platinum powder that can break down the fuel into electrons and ions. And then the catalyst, usually made from nickels, that converts ion into waste chemical, with water being the most common type of waste. Gas diffusion layers that are designed, and last is the gas diffusion layer that are designed to resist oxidation. For better fuel cell, the fuel cell stack size must be considered for the power requirement, and then the number of cells to determine the maximum voltage that are required, and then the stack configuration. This is the simple polymer electrolyte membrane fuel cell. As you can see here, this is the simple polymer electrolyte membrane fuel cell configuration. Some of the fuel cell important component is the efficient airflow that filtered particulates as it being pumped into the fuel cell from the atmosphere. And then the hydrogen flow, which control the pure hydrogen that are stored in a compressed gas cylinder. And then the water and hydrogen out, which allow the hydrogen to exit the fuel cell stack by going through a particulate filter. There are a few additional sensors that are used in the fuel cell configuration, such as thermocouples, pressure transducer, methanol or hydrogen sensor, and mass flow controller. In a fuel cell, there are fuel subsystem. The fuel subsystem is very important because the reactant need to move around the fuel cell to be pressurized, cooled, heated, and humidified before ultimately be delivered to the fuel cell. The fuel system allow the reactant to accomplish this task by using blowers, compressor, pump, and humidification system. Other plant components such as turbines are also used because they can harness energy from the heated exhaust gas from the fuel cell. There are many components that are used in fuel subsystem. For example, is the fans and blower. It is an economical way to cool a fuel cell or to provide air to the fuel cell. When fans and blower were used, the fuel cell exhaust is open to the environment. The fan or blower is driven by an electric motor that requires power for the fuel cell or another source to run. One of the common used fans is the axial fan that are effective in moving air over parts, but it is not effective across large pressure differential. Next component in the fuel subsystem is compressor. Compressor compress the air input to increases the concentration of oxygen per volume per time, and therefore can increase the fuel cell efficiency. This means that a lighter and smaller fuel cell stack can be used instead of a bigger one. In addition, the drop-off in voltage by mass transport problems is delayed until a higher current densities. If the pressure is higher, a lower volumetric flow rate can be used for the same molar flow. Because the compressor compresses the air, humidification is also easier since less water is required for saturation per mole of air. The flow field design is less restrictive because larger pressure drops can be tolerated in the flow field by using compressor. A compressor that like a fan or blower is driven by an electric motor, which does require power for the fuel cell or another source to run. Next is the turbines. In a pressurized fuel cell system, the outlet gas is typically warm and pressurized, though it is lower than the inlet pressure. This hot gas from fuel cell can be utilized to turn into mechanical work through the use of turbines. This is like a turbo in a ICE engine. This energy can be used to generate work that may offset the work needed to compress the air. The efficiency of the turbine determines whether it should be incorporated in the fuel cell system. As you can see here is the figure showing gas turbine in the fuel cell vessel. Next is the humidification system. In fuel cell, humidification is needed, such as in a PEMFC system. A humidifier for the hydrogen gas inlet stream is required to prevent the fuel cell PM from dehydrating under load. The water management is a challenge in the PEM fuel cell because there is ohmic heating under higher current flow, which will dry out the polymer membrane and slow ionic transport. Stacks that are not operating near the maximum power constantly may not require humidification, or the stack may be able to self-humidify, but if the stack are constantly operating near maximum power, it will be drier and humidification is needed. In larger fuel cell system, either the air or the hydrogen or both the air and hydrogen must be humidified at the fuel inlets. The gases can be humidified by bubbling the gas to the water or steam injection, exchange of water and heat through a water permeable medium, or through many other methods that are currently available. Last but not least is the fuel cell pumps. Pumps like blower or compressor and fan are among the most important components of the fuel cell plant system. These fuel cells are required to move fuel, gases and condensate through the system and are important factors in the fuel cell system efficiency. For a small to medium sized PEMFCs, for portable applications have a back pressure of about 10 kilopascal or 1 meter of water. This is too high for most axial or centrifugal fans. Therefore, a pump would be better suited for these instances. Thank you.